Morning, everybody. Hi. Okay, this is Papa Lim. Okay, welcome to another session of Papa Lim Physics Classroom. Okay, today we'll be going through the exam paper for the Sec 4 Express. Okay, the science physics paper. Today paper will be, I'm using Hua Yi 2021 paper. Okay, if you need the paper, is in my description below. It's in my Google Drive. Okay, you can take a look at the paper and try for yourself to see how much you have mastered and what are the common mistakes that you have made, okay, in the process of your revision. Okay, now without delaying, okay, I will go through the paper for every question for paper 1 and 2. Okay, same as before. Okay, if you need certain questions, okay, just drag to the respective timeline. Okay, don't need to watch through the whole video. Okay, because it's a long video. Okay, because it consists of all the questions. Now here we go. Okay, this is the paper. Okay, it's a good paper. Okay, the setter has set up some interesting questions for the students, and some of the questions in the paper actually deal with some of the common mistakes that students make. Okay, so you actually try out the paper. Okay, for paper 1, I leave the answer here. You can pause the video here and take a look at the answers. Give me a minute. Okay, yeah, here you go. Okay, here you can pause the video here and take a look at the answer and check which are the MCQ questions that you actually got wrong. Okay. Now, without delaying, okay, we'll look at paper 1 first. Okay, question 1. Now, question 1 is I would say it's a straightforward question. It's a very common trick that we always like to use. Okay, for example, right, the question will give you a vernier caliper, how to read the vernier caliper. So same thing, okay, students, you need to know how to read the vernier caliper. Okay, so this is 1, below is 0.5. So every unit on top is represented by, every line on top is 1 unit. Every line below is actually represented by 0.5 units. So this is read as 1, 1.5, 2, 2.5, and 3. Okay, so the main scale that you're looking at is 3. Okay, it's a 3 mm. Okay, then after that, the line that you are looking at here is 0.3678. Okay, so it'll be 3 plus 0.38. Okay, so the total unit that you're looking at here is 3.38 mm. Okay, now for the segment here, is you must be careful, is that 3.38 is actually not the answer yet, because the question says that it is actually a measurement of 20 pieces of paper. Okay, 20 sheets of paper, and the question asks for the thickness for 1 sheet of paper. So once you've gotten this number here, actually, okay, remember to divide by 20. Okay, to get the number for the single thickness. Okay, because the question gives 20 thickness for 20 pieces of paper, 20 sheets. I only want 1 sheet. Okay, the rationale for this you have to understand is that sometimes that although micrometer screw gauge is quite an accurate instrument with a high precision, but 1 piece of paper or 1 sheet of paper, it could be too thin to be measured accurately. So one of the things that we always do is, instead of measuring just 1 sheet of paper, we actually get a certain sizable thickness, maybe 20 pieces of paper, 20 sheets, 30 sheets, okay, so that we can measure a thicker length and actually reduce the error. Okay, so that's why we are able to get, we are using a large number of papers to actually get the size, the more accurate measurement of the size of a single piece of paper. Now, vector quantity, I will not deal with too much. Okay, all physics student, you should know. Now, for question 3, take note, question 3 we are looking at is the drawing. Okay, the car is moving to the right, okay, as mentioned here. And you look at the spacing of the dots, okay, while the car is driving, the oil is dripping down. And the oil drip, okay, look at the spacing of the oil here. They are actually of the same distance. So which means the car or the oil is being the oil is dripping at a constant rate, and because of the dimension, the interval of the car of the oil drip, okay, it's actually equal spacing. So this spacing here is actually equal. So it will mean that the car is actually moving at the same speed or at a constant speed at these particular instances. After that, you start to take notice is that the interval actually becomes smaller and smaller and smaller. Okay, the interval here becomes smaller and smaller and smaller. This will represent that the car actually is slowing down. Okay, the oil is actually dripping at a constant rate. But because the car is slowing down, okay, the oil drip, the distance between the drips, each drip will actually be closer and closer and closer. So what does this tell you is that at the beginning, okay, the car is actually moving at a fixed speed. Okay, it's a constant speed. After that, okay, he starts to slow down. Okay, at this junction here, because the dot is getting nearer and nearer. So the only answer that fits the description will be the car is moving at steady speed and it's actually slowing down. Okay, the reverse, if it's getting is it increasing, you find that if it's accelerating, the dot will actually be spaced out further and further and further and further and further apart. Okay, so this is it's a quite interesting question, okay, that we don't normally see, but it's really a good question to test to students how they interpret from pictures to the common questions that we have. Okay, or the other one that we look at is this particular question. Okay, the question here involved that is dealing with Newton's law, F equal ma. The question says that it is exerted a constant horizontal speed, okay, on the particular object here. So the force is constant, is being added. Okay, it's being pushed to it's being applied onto the trolley and the masses actually changes. Okay, based on the graph, the mass of the trolley and the masses are actually increasing. So as I increases, you find that the acceleration of the objects actually decreases based on the graph. Okay, and what happens is when I accelerate, the mass is decreasing. Okay, what this implies is that the important clue that the question tells us is that the object is applied, if the object is applied, okay, a constant speed is applied to the object here. So which means the force is actually on the left hand side is actually a constant value. Okay, what does this graph tell us is that for the respective mass, example for a mass of 1.2, okay, the but respective acceleration will be this value. Okay, same thing if I have a mass acceleration of a mass of 1 kg, the respective acceleration will be 0.8. The common thing between these two values is that at 1 kg, the acceleration is 0.8 meter per second squared. At 1.2 kg, the acceleration is roughly maybe, what was the number here? Is 0.6, roughly here, 6, 2, 4, 6. Okay, let's say around 0.66 meter per second square. Okay, so what does this value means that for respective value, for respective mass, there will be a relevant accelerations experienced by the objects. And but one thing common between them is that regardless of the mass and accelerations, okay, the force applied on both situations is always the same. Meaning, if you multiply based on the formula, if you multiply the mass and the acceleration for both cases, they will give you the same number. Okay, so what we are doing here is we are looking at different values of mass and acceleration, but one thing constant among all these different numbers here we are looking at is that they always have a same force, okay, applied onto the object itself. So what we are doing here is that if I have the mass, let's say example I choose let's say I choose 1 kg, my acceleration is 0.8 meter per second squared. Okay, so if I substitute into the mass, I substitute into the acceleration, I multiply them together, I'll get the force to be 0.8 Newton. And this is the force that is applied to the object at that particular instances. And same like what the question mentioned, since the force is constant, if you look at this number here, if you multiply the number, you will also get back the same number, which is 0.8 Newton per kg. Okay, so what this graph is trying to tell students is that if you look at the graph, although the mass is different, the acceleration is different, but these two factors has a common phenomenon, have a common relationship between both values, is that the product of these two numbers will always give rise to the same value. What value are we talking about? The constant horizontal force. Okay, so when you look at the questions, okay, what the questions need from you for question 4 is actually to allow students to actually take time to interpret the graph and to interpret the relevant or to infer the relevance of the correct data. Question 5 also has the same meaning here. It deals with pressure. Pressure is F over A, okay, force per unit area. Okay, what the question here is that the blocks is being stacked higher and higher and higher. Okay, so as the weight of the object actually increases, okay, the pressure of the, based on the formula, as the force at the weight of the object increases, the pressure of the object will be increasing. The pressure exerted on the floor will also be increasing. But what is interesting about this is that the bricks are being stacked on top of each other, which means the area exerted, the perpendicular area that we are looking at, is always a constant value. So which means if I multiply, if my force or my bricks actually double, the weight double, you'll find that the pressure will actually double by the same amount. Okay, so which means the increment experienced by the weight itself, by the force itself, okay, will actually be directly translated to the increment in the pressure. Okay, so if I increase the weight by 2 times, the pressure will increase by 2 times. So if I increase it by 3 times, the pressure will increase by 3 times. So the increment is actually constant. Okay, so there will be increment. So which automatically C will not be the answer. Pressure will have to be increased as weight increases. And because you know that the force, the weight increase and the pressure increase is always by the same value. So it will definitely be, it will not definitely be A and B, because A and B, you'll find that the pressure actually increases at different rates. Okay, so the only answer that has the same, the fits the description, whereby the force increases and the pressure increases, and the force increased by the same, by 2 times, the pressure increased by 2 times, the increment is the same value for F and P, will only have to be option D. Okay, it will be a straight line moving upwards. Okay, because the increment, let's say for example, my mass, my weight increases by 2 times, my pressure will increase by the same proportion. Okay, so this graph will fit the relationship, will fit the condition specified by the question. Now, question 6. Okay, graphites. Okay, large graphite stone, small graphite stone. Okay, now which of the object weigh more? Okay, based on the questions here, you will need to take note. Okay, now which of the object weigh more? Okay, and why? So based on the questions, you take a look. Okay, now the box that we are looking at is, we are looking at the same volume here. Okay, so what you're looking at, which of the object will weigh more here? Obviously, okay, if you look at the question, here, okay, the object, the one with the more graphite chippings, all these things will definitely have a larger mass. Okay, why? Because if you look at the spacing between them, okay, if I have a small stones, you have big stones versus small stones, the difference is the amount of air being trapped there. Okay, for big stones, okay, if I have big stone inside, the air inside, the air spacing, because of the size of the stone, the air gap here is actually bigger. Okay, the air gap here is bigger, and because the air gap here is bigger, okay, it means that the number of stones I can keep inside X is actually lesser, as compared to Y, with the gap is actually smaller. The gap is actually smaller. And because I have smaller, I will be able to squeeze in more graphite stones, graphite chippings, all this inside that particular container. Okay. And as a result, I will know that C will actually be the heavier box. Okay. Because of that, I'm able to compress them together. Now, take a look. Okay. You take note that the 2 stones, although they are chipping and stones different in sizes, but they are graphites. So between they are the same material, so which means automatically I will know that the density of the chip, okay, will definitely be the same, okay, because they are the same material. Okay, so therefore I will know that B and D automatically will not be the answer. Okay, and with that I will be able to narrow down on the answer to be A and C, and with the air gap in mind, okay, you will know that, okay, C will be the most appropriate answer. Now, for 7 is a very good question. Okay, 7 is dealing with elastic questions, which we don't see common, but that's why we need to pay attention to this type of question. Now, for a spring here, based on the question is the spring is being put down to R. Okay, so which means at R the spring is extended. the spring here is extended. Okay. Now, after that is move up and down, all these things. Okay. And they tell you that the highest point is P, the lowest point is R. Now, here what we do is we know that it is being extended. Okay. And after that, it starts oscillating or it starts moving up and down between P and R. Okay. So P and R will be the highest. P will be the highest position. R will be the lowest position. Now, for oscillating, take note is that between the highest and the lowest, the middle segment will be actually what we know as the equilibrium position, or what we call the original position. This is where the original position is, which means this particular location, the middle, okay, it will be the length of the particular, this length here to Q. This will be the original length of the spring. Okay, these are some facts that you have to know. Original length of the spring, another name for it is what we call unstretched. Okay, unstretched length. Okay, which means if the object is at P, okay, means at P, this is what we call the maximum compression of the spring. When the spring is being compressed, and at R, okay, the lowest position, what does this mean at the R? This will be what we call the maximum extension of the spring. Okay, so usually when we talk about oscillating, okay, there are actually 3 points that you need to take note is where the original is, the original length, followed by the maximum compression, and followed by the maximum extension. Okay, so when we talk about the, and how do we know the maximum compression is usually paired with what we call the highest point in the oscillations. And how do I know is the maximum extension? Okay, it means that most stretch position is always paired with the lowest point in the oscillation. Okay, so between these two highest and lowest, in between them will be what we call the original length. And at these 3 points, there will be certain characteristics that student has to take note. For example, at the highest point and the lowest point, okay, for oscillation, you have one characteristic is that the speed of the object is actually 0. Okay, the speed of the object here is actually 0. Okay, primarily because at the highest and the lowest position, okay, the object has to be at 0 because it's about to change direction. So at the highest position, before it starts coming down, he must slow down, he must reduce the speed to 0 first before I change direction. The same thing at the maximum, at the lowest point, the maximum stretch. Okay, before I shoot up, before I change direction, I have to slow down. I have to stop for a while first, a split second before I move up, before I change my direction. So at the highest and lowest point, you'll find that okay, the speed of these 2 points, the speed at these 2 points for this object is actually 0 meter per second. And similarly, at the middle section here, at what we call the original length, the speed is actually what we call the highest. Okay, it will pass through the original position, the unstretched length at the maximum speed. Okay, and this is what I mean by when you look at spring oscillations, there are these 3 points that you students have to take note. Okay, when you're looking at oscillations. Okay, so with this in mind, you will be able to look at what is happening. Okay, and why? Because with this information, 0 meter per second, 0 meter per second, and maximum speed, you will be able to infer that at 0 meter per second, which is the highest and the lowest, the kinetic energy here will actually be 0, or what we call the lowest. Okay, likewise for here will be kinetic energy will be the lowest. And of course, the kinetic energy here will be maximum at the middle section. Okay, so these are the characteristics for oscillating that the student have to take note for. Okay, so these are some of the factors or some of the characteristics that we need to take note. So with this, I will be able to answer that. The answer will be Q, okay, with the highest kinetic energy. Okay, so that's why I say this question is actually quite an interesting question. Now, question 8. Okay, question 8. Okay, the object is dropped 40 meter per tower. Okay, 40 meter tower drop. Drop means initial object, initial speed is 0. Okay, if I say throw, it will mean that the initial speed, there's a number. But drop don't have. Drop means it's stationary, it's just release. It will start from 0 and it will start to increase. Now, so which means at the object which is 40 meter high, okay, so it drop all the way down. Okay, so what the question one is, what happened when it's at 10 meter here? What happened to the kinetic energy at 10 meter here? Okay, originally it's 40 meter. Okay, 40 meter high, let's look at the energy possessed. At the beginning, before I drop, you will definitely have a potential energy, okay, due to 40 meter. Okay, at 10 meter here, you will take note that the energy I'm looking at, the potential energy I'm looking for at is only worth 10 meter only. Okay, so the ratio of kinetic energy to the potential energy. So what happens to the conservation of energy? So at this final position, which is 10 meter, okay, I'm only left with 10 meter of kinetic energy. Okay, which means that the 10 meter of kinetic energy, what happened to the rest of the energy? Okay, and what is the rest of energy? Originally, I started with 40 meter of potential energy. Now I'm left with 10 meter of potential energy. Okay, so which means at 10 meter, okay, the potential energy is actually worth 10 meter. Okay, and so what happened to the kinetic energy? What happened to the kinetic energy is this is what we call conservation of energy. Okay, at the beginning, I have 40 unit, I have potential energy due to 40 meter, and at the end of the day, I have potential energy only worth 10 meter. So the remaining kinetic energy is actually, okay, where does the remaining kinetic energy come from? Okay, it's actually converted by the potential energy, from the potential energy. So the remaining 30 meter worth of potential energy, okay, is actually converted to kinetic energy, okay, ideally. Okay, so that's why I will know that the potential energy at 10 meter will be, like I would say, just 1 unit, okay, 10 meter. And the remaining of kinetic energy, I will not know the number, but I actually know how much, where can I get it? I got it from the potential energy, which is worth 30 meter. Okay, so if 10 meter is 1 unit, 30 meter will be roughly 3 unit here, will be 3 unit. So the ratio of the kinetic energy, so the potential energy at 30 meter is actually converted to kinetic energy. So I will know that the kinetic energy and the potential energy in terms of ratio, it will be 3:1. Okay, so I would say it's interesting, okay, simple but yet interesting question, okay, to look at conservation of energy without doing any calculations. Okay, now for 5, okay, highest average speed. Okay, you look at thermal property, highest average speed usually involve around temperature. The higher temperature, okay, the higher temperature, the higher is the kinetic energy, and the higher is the velocity. So straight away, we'll just look at the object with the highest temperature, and I will know that that particular object or particular state will definitely have the highest velocity, which is D. Now, question 10. Okay. Now, question 10, nothing much, is talking about convection, current, and radiation. Okay. Position up and down will be convection. Okay. Sun and earth, take note. Sun and earth means in between is vacuum. Okay. The only way energy is transferred through vacuum, there's only one way, which is radiation. Okay. So I would say this question is quite straightforward. Okay. You'll be able to know that this will be convection because of the placement of the object, top and bottom. Okay, hot rise, cold sink. Question 11. Question 11 is quite a common question that we see in the exam paper. Okay, to looking at the motion of the particle. Technique is always the same. Okay, you take note of the wave direction. Okay, so at this particular instance, the question says that the wave is moving to the right. So how do we identify the movement of P and Q? We look at the next instant. Okay, let's say slightly, maybe 0.1 second later. Okay, the object is moving to the right. The wave is moving to the right. So 0.1, let's say a split second later, the wave will be actually moving to the right. Okay, like what the question mentioned. So the wave will be somewhere in this motion. Okay, so the red color one refer to the wave at the next instant. So example, if black if the black one is time equal to 0 second. So the red one, it could be time equal to 0.1 second, just a split second later. You'll find that, okay, as we all know that particles can't move. They will only vibrate about their fixed position. So at this junction here, you'll find that originally P was at this location. Okay, so now at 0.1 second later, P is here. Okay, then after that, same thing as before, Q was here at the beginning. Then after that, 0.1 second later, at the same location, Q actually is here. Okay, so you'll be able to see that actually between 0 second to 0.1 second, P actually moved downwards to P1. Q actually moved upwards to Q1. Okay, so this is what we mean by we are able to identify the movement of the particle. Okay, just by looking at the next motion. Okay, next instance. So I will be able to take it as P is moving down, Q is moving up. So the answer will be D. Okay. So the technique is actually it's always this technique whereby you look at the wave motion. If it's moving to the right, you shift the wave to the right for the, let's say for the 0.1 second to identify how the object or where the object is moving. Okay, refracting index. Okay, question 12 is a straightforward refraction question. Okay, whereby we look at sine refracting index is sine of what we call the angle in the less dense medium divided by sine angle in the dense medium. Here, take note, I would say that most students will know this is what we call the dense medium, the glass block. The air is actually the less dense medium. This one, no problem about that. But what tricks, the common trick that we always try to trick students is that the angle for light ray, remember, is always has to be measured from the normal to the ray itself. So in this question, although I'm given 30 degree, but the number that I should substitute in the numerator here, okay, it cannot be 30 degree. It has to be 60 degree because light ray is angles. Okay, it's always measured from the normal to the ray itself. Okay, so it has to be 60 degrees. So if you substitute the number, you should be able to get the answer straight away. Okay, so I will not dwell too much on that. Okay, so just take note of the common tricks that we use. Okay, the angle, please use the correct angle. It always has to be measured from the normal and to the ray itself. Okay. Now, take a look at these instances. Okay, you will not see this diagram quite often, but you will see this characteristic very, very often. Okay, in the textbook that we have or in the notes that we have, this is what we call a virtual ray. Okay, how do you know a virtual image? Okay, because of one thing, the ray here is dotted. Okay, some of the common convention that we have is, sorry, excuse me. The convention that we have is we have dotted lines, okay, to represent virtual rays. Okay, and the only time whereby you have virtual ray is whereby this object O, okay, object O, okay, the distance of the object O, whereby I have virtual ray, it must be slower, it must be smaller than the focal point, okay, or what I call the focal length. Okay, so this is the only case whereby you have virtual ray. And same thing, principal focus, okay, occur where? Principal focus occur at focal point. Okay, so I will know that if the for virtual ray to occur, it has to, object distance must be less than focal point. Okay, or what we call the object, the distance of the object must be less than what we call the principal focus. What happened to my spelling? Okay, Principal, principal focus. Okay, so this is the characteristics, okay, for virtual ray. So the option would be D. Okay, 14, we look at the sound travel. Remember for sound travel, okay, sound travel, okay, speed of sound. Okay, we always have to take note, speed of sound is always fastest in solid. Okay, slowest in gas. Okay, so we have to take note of the separate medium. Okay, now, so what happened is 2 seconds later after the fan is being struck, okay, the object hears the girl hears a sound through air. Okay, so what happened is the question asking for what happened to how long does it take for the sound to reach the girl through the fan. Okay, so there are actually two traveling mode. When the boy hit the stick on the fan, sound actually travel to the girl in two different paths. One path is through the solid, okay, which is through the fan directly. Okay, the other path that the sound actually travel to the girl, from the boy to the girl, is actually through the air. Okay, so through the air, okay, to the girl. So there are two separate paths that we are looking at. But okay, so this is what the question is trying to highlight to you. This is what the story is trying to tell students. So what happened now is the moment the moment the boy strike the fan, okay, the moment time strike the fan is what we call time zero. Okay, the girl will definitely hear a sound, okay, through the fan, okay, the solid itself. Okay, but of course there will be a time delay. It's not like immediate. So confirm the girl will not hear the sound straight away through the fan. It will not be 0 seconds. This is not instantly. Okay. So it will definitely not be 2 seconds, because 2 seconds later, the girl actually hear the sound through the air. And we know that through the air is actually the slower path. Okay, so confirm, if I hear the sound through the fan, which is the faster path, it must arrive through the ear to the girl, okay, at the instance less than 2 seconds. Okay, exactly what is the number I will not know, because the question doesn't give us more values to investigate. But I will definitely know that the girl will definitely hear the fan, the first sound, which is through the fan, at an instance less than 2 seconds. Then after that, at 2 seconds later, based on the question, okay, the girl will hear the sound through the air. Okay, so that's why the answer here is B. Now, for charging, okay. Now, based on the question this is quite a common phenomenon that we see, not just in this particular question, but we are looking at maybe spraying of fertilizers or even car spray paints. All this, you'll find that the soap, okay, bubble, or the spray paint or the fertilizer bubble, or everything actually move away from each other very, very fast. Okay, when we're using a charged particle to spray out. Okay, so what actually happens is, because the air particle, the particle that we are looking at doesn't, I will not say it has to be negative charge, basically. Okay, but it's very, very commonly that the bubble has to be negatively charged, but it's easier to get negatively charged rather than positively charged. But one thing confirmed is that regardless of positive or negative, okay, charge, the particle, the soap bubbles, okay, so, or the fertilizer bubble, or even these car spray paints, okay, when they move away from each other, is because all the bubble, the moment they leave the system, okay, these bubbles are actually charged, okay, to the same unit, okay, to the same pole, okay, polarity. Okay, so they will all be having the same polarity, which means all of them will be either, everybody will be commonly positive charge, or you'll be commonly negative charge. Okay, and why? Because of why do I want to charge them to the same polarity? Because when they are all the same charge, the bubble will actually repel each other. Why? Because light charge repel. And when I repel them, the bubble or the spray paint or the fertilizer can spread to a bigger distance. Okay, I can actually cover a bigger area. Okay, so one of the statement is correct, is that positive charge and negative charge, they are somewhat correct, but they are not always the case. Okay, because it can be negatively charged, so it can be positively charged. So the answer that is more encompassing will be actually option D, whereby the bubble will actually have the same charge, okay, as the students. Okay, so all the bubbles will all be holding on to the same charges. Okay, because light charge, they will repel. So same charges here, that doesn't mean plus or minus. It depends on the question itself. So in most cases, it will be negatively charged, but there are cases whereby it is positively charged. Okay, so I would say A, B, and D. D will be more encompassing. Okay. Now the current. Okay, how long does it take? Okay, question 16 is an easy answer. It's an easy question, but it requires students to take note of two things. First thing is the formula. Current is the rate of flow of charges, which is Q over T. And after that, students need to take note of the prefixes, milli. Okay, 35 milliamp. Okay, SI unit. This is not SI unit yet. There's prefixes milli. Milli means divided by 1000. So it's actually 0.035 M. Okay, if you don't want to change milli, okay, why? Because I will not want to change the milli in this case. Why? Because the option given here is all in milliseconds. So the conversion is the milli is still there. So I can actually just ignore the milli. Okay, so you can just put 35 here. Okay, 35 divided by time. What's the current? Sorry, my mistake, not 35. Okay, the current here, the current is 35 milliamp. I'll leave the milli inside. Okay, and the charge given is 70 micron. Okay, now micro here, okay, is 10 to the power minus 6. Okay, so take note of the units here. Okay, so it's 10 to the power minus 6. Okay, so if you pump me all the number, you get the respective answer. That is the correct answer appearing. Okay, if you have problem with dealing with preferences, my advice is actually convert everybody to the same SI unit. So instead of using milli here, I will just convert. Let's say if I convert, this will be 0.035 milli. So I convert the milli, okay, to SI unit. I convert the micro to the SI unit. Then after that, I put in my calculator. It will be in SI unit, will be in seconds. So the time given here will be in seconds. Okay, then after that, I will just convert the seconds to milliseconds respectively to get the answer. So prefixes, chapter 1, okay, you have to know your prefixes, and not just knowing how to calculate, because sometimes I do require students to actually convert the prefixes themselves. Okay, 17, nothing much, just standard SI unit. Okay, standard definition. Now, 18, the EMF is 2 volts. Okay, you have arrangements. Okay, 2 parallel, P and Q here is actually parallel to each other. Okay, then after there's a current of 2 amp flowing through. Okay, so since this arrangement, 2 amp will be flowing through here. Okay, the current 2 amp will be flowing through here, and actually after that, at this junction here, some current will go up, some current will go down. So the current 2 amp will actually split into 2 paths, one up, one down. And I know the top path is 0.5. So automatically I know that this path will be 1.5 amp. Okay, because the current will actually split. Okay, 2 amp will actually split into 0.5 and 1.5. Okay, so straight away, okay, take a look at the current. So the question says, what's the resistance of P and what's the reading for voltmeter Q? Okay, so I want the resistance value P. Okay, so based on the question, this is 0.5. Okay, so I will know that this is EMF is 0.5. Okay, and this potential difference, I will call this V parallel. Okay, so based on the calculation, I will know that the EMF, okay, the EMF, it consists of 0.5 volts, which is here, plus V parallel. Okay, and based on the question, EMF is 2 volts, 0.5 volts plus V parallel. I will be able to get the V parallel is actually 1.5 volts. So since V parallel is 1.5 volts, okay, and V parallel will also be the same potential difference as Vp, potential difference of resistor P, which is controlled by V equal to IR, P, IP. Okay, so if I know that Vp is 1.5, IP, which is, this is IP, 0.5. I will be able to calculate the resistance value for resistor P, which is 1.5 divided by 0.5. If you press your calculator, 1.5 divided by 0.5, it will be 3 ohms. Okay, so automatically it will be B or C, whichever. Now we still can't get the answer yet. You can only isolate the answer to be B or D. So now we look at the next part, the reading on Q. Now, potential difference of Q, okay, because these two branches are in parallel, because potential difference of P, potential difference of Q, they are in parallel with each other, so they will have the same potential difference of V parallel. So the equation will look like this: Vp, and after it will be equal to V parallel, which happens to be, this number happens to be here, okay, which happens to be 1.5 volts. Okay, so VQ is actually 1.5 volt, which is here. So answer will be C. Okay, so this question require you to do a bit of calculations, okay, and actually require you to understand the property of circuit, okay, of parallel branches and the series branches. Okay, so take note of your circuit, okay, know all the formulas and know how the relationship between series and parallel in terms of currents, potential difference, and resistance. Sorry. Okay. 19. Okay, question 19. Things to take note is I have a 30 amp fuse. Okay. And the ideal current or the working current is actually 2 amp. Okay, so at the fault occur, okay, and the current increase to 5 amp. Okay. Is an overcurrent here. Okay, it's definitely a fault. Okay, now, but take note now is that the fuse is 30 amp. So even though there's a higher current, there's a high current here, because the current is still lower than the rated value, which is 30 amp, the fuse will not activate. Okay, I won't, because the fuse will only be activated, the fuse will start to melt only when the current is above the rating, which is more than 13 amp. Okay, so that's why I will know that C would not be the answer. Okay, I will not receive electrical shock because why? Because electrical shock usually referring to that if I touch the casing or if I touch the wire, okay, the current will actually flow through my body. Okay, but in this case, there's no leakage of current. Okay, based on the question, the only fault that we're dealing with is the current is above the normal. Okay, so shock will definitely be out. Large amount of electrical energy is wasted. Oh, I would not say it's wasted. There's no much clue here. Okay, but I would definitely know that because now the current is actually higher than what is being designed. Okay, so I will definitely know that the current, the 5 amp current, I will know that the cable will be getting hotter and hotter. Okay, it will be hotter than the usual. Okay, and eventually, okay, look at hotter. Okay, the cable may start a fire. So D will be the most logical choices here. So this is one of the danger with using current that is like much higher than the rated the fuse that is of using fuse that is higher than the possible higher current. Okay, because if I use a fuse that is much higher, okay, much higher than what a normal fault current will be. For example, if I design a 2 amp cable to hold 2 amp, okay, but if the fault occur and it's only maybe the common fault I'm looking at is only 5 amp or 6 amp, okay, but my fuse I use a 30 amp. Maybe my fuse rating is too high already. So my fuse rating too high, what happens is when the fault occur, the fuse will not melt, it will not cut the circuit off. So what happens is I will still experience heating in the cable, and eventually I will still have electrical fire happening, even though I have the safety precaution, the fuse implemented in the circuit there. Okay, so that's why it's necessary to use the correct fuse rating for your appliances. Okay, tripping plug. Okay, so you take note of the fuse rating here. Okay, standard things they have to take note. Okay, the fuse is always connected to the live, so this is definitely correct. Okay, then after that you will have different cable. Then after that, just take note. Okay, check earth cable is connected to the top. Yes, correct. Okay, then after that, the neutral cable is here, is connected on the left, is correct. Yeah, everything is correct. Okay, so what could be the possible fault that we're looking at? Okay, which is here. Other than the 3 cable in the circuit, what we are looking here is actually the cable here. The purpose of this item S, or what we call the cord grip. Okay, now the cord grip that we're looking at C, the purpose of the cord grip is actually to grip the cable. Okay, the cable, the casing. Why I want to make sure that the cable, okay, the insulation, everything should be under this cord grip here. Okay, because the main purpose of the cord grip is actually to grip the wire, so that in case external factor, let's say if I pull the wire outside, if I pull the cable, okay, the whole 3 wires inside will not fall out straight away. So the cord grip, the purpose of cord grip is to secure the cable to the plug itself. So the cord grip S, okay, must secure, okay, the cable here, the insulation, together with the insulation, so that I can actually secure the wire to the grip itself. So that's why the arrow here we are looking at is actually A. The cable cover, okay, is not under the clip S. Okay, S is cord grip. Okay, so we have to make sure that for electrical wire, electrical plug, okay, other than the wires are being screwed to the correct places. Okay, the cord grip and the cable must be actually at the correct position also. Okay, so this is one of the common fault that we actually deal with in real life actually. Whereby the cable is actually also to be exact, the cord grip is actually not gripping the cable correctly. And as a result, whenever I pull the cable, all my earth life neutral wire all will come out already. Okay, and it become a hazard here. Okay, so with this, we will move on to paper 2. Okay, paper 2 here. Okay, paper 2 here is a vector addition. Okay, there are two forces given, and based on the questions, okay, these two forces are given. Okay, so simple vector additions. The easiest way to use parallelogram method. Okay, if you forgot how to use parallelogram, okay, I make a detailed video on parallelogram method and tip to tail method. Okay, on vector addition. Okay, on if I'm not in chapter 3. Okay, you can look at the video. I will share the link below later. Okay, if not, you can look at my my channel under my playlist chapter 3. There's there's actually 2 or 3 questions on that. Okay, now for tip to tail, same thing. Okay, so once what we are looking at is the drawing. Okay, to come up with 2 parallel lines. Give me a minute. Yeah. Okay, so let me rotate the thing first. Okay, so for 450, okay, so same thing. Make sure for first part drawing, okay, make sure when you draw the forces, okay, make sure it's single arrow and you label all the forces. So what you do now is you actually produce 2 parallel lines. First one is here. Second one is here. Okay, make sure, okay, these two is the same length. Okay. Then after that, the second line, okay, okay, drag here. Now, these 2 line here, okay, take note, do not right arrow. This should be, it can be solid or dotted line. These are your working line. Okay, they represent the working line. They don't represent the force. So don't go and put arrow here. After that, you will find that the intersection between these 2 points, which is here, or what we call the end point, this is where the resultant force will act on. So from the beginning, okay, use a ruler. Okay. Then after that, put a double arrow here to symbolize resultant force. Okay. Then after that, take a ruler. Okay. Measure the length here. Okay. Take a ruler. You take a ruler, measure the length between the 2 objects. Okay. Measure the length here. Okay. This magnitude of the length will be the magnitude of the force. Okay. That is given, or of the resultant force. That's what the question is asking for. Okay. That's how we do vector additions, how we look at using parallelogram method. Okay. For the sake of time, okay, I will not use the tip to tail method, but if you need, okay, I have the video done in, like I mentioned before, I have the video done in my chapter 3, okay, in the chapter 3 playlist. Okay, you can take a look at how I use, or how you can use tip to tail to add forces together. Okay. Now, for question 2 is a moment question. Okay. Now, clockwise and anti-clockwise moment, there is a few forces that we're looking at. Okay, the pivot, based on the question, the pivot is attached at one end. Okay, so the pivot is at O. Okay, based on the question, the pivot is at O. So this is my pivot. Okay, so what happens is there are a few forces acting here. Okay, one is force T. And after that, there's a weight of the object, 150 Newton. Okay, now take note, is 150. I would say the 150 Newton with respect to the pivot, this will be a clockwise moment. Okay, I will label it M1005. This will be a clockwise moment. The perpendicular distance will be 3 meters here. Then I will say it's quite straightforward. Okay, so this is the first force that is 150 clockwise moment. Now, based on the question here, there is another force that is appearing, that is mentioned, but it's not drawn in the picture, which is your beam. The beam is 2,100 Newton. Okay, the beam that has a weight is 2,100 Newton. And where is the beam? The beam length is 8 meters. Okay, and based on the question, it's a uniform beam. So which means the CG is at the center. So I will know that the CG, okay, is at 4 meters directly. Okay, so it will be somewhere here. So which means the weight of the, let me clear your way, it's a bit messy here. So I would say this is the clockwise moment, M1500. So the weight will be here. This will be the weight of the beam, which is 2100 Newton. Okay, and weight of the beam based on the, with respect to the pivot, it will also have a clockwise moment, M2100. Okay, and the distance between them, it will be 4 meter. Okay, so total clockwise moment for this question here, there are two of them, which is your moment due to your 1500 Newton and the moment due to your beam itself. Okay, so if you multiply correctly using the correct distance, 3 meter and 4 meter, you get answer 12,900 Newton meter. Okay, now, same thing, definition, principle of moment. Okay, remember the definitions and remember keywords that we have is you have to state the same pivot. Okay, some of the keywords that you must remember when you do the definition. Then after that, the question says that show that the tension is 3,225 Newton. Okay, so here we take principle of moments whereby you take a sum of clockwise moment equal to the sum of anti-clockwise moment. Okay, and they have to be balanced because the question said everything is in is balanced. So the problem here is where do I find the anti-clockwise moment? Clockwise moment is settled already. Clockwise moment is here. Okay, so this will be the clockwise moment. Okay, so where is the anti-clockwise moment? Okay, let me erase it. Anti-clockwise moment is because of this guy. Okay, your tension T. Tension is here. Okay, so the T is here. Now, but take note the T, okay, the perpendicular distance with respect to the pivot for force T is not 8 meter. It is not. It is not because T is not the perpendicular distance. Okay. So same thing is where do you find the perpendicular distance? Is the technique here that I mentioned before in chapter 5. Okay. Is what happened is you take the line of action of the force, this black color line. Okay. So you copy this line, you move it to the pivot. Okay, you move it to the pivot. Okay, now between these two lines, what you need to do is you put your ruler between them. Okay, you put the ruler between them. The shortest distance between these two lines will be what we call the perpendicular distance. And the shortest distance between these two lines is actually the red color one, which is your 4 meter. So 4 meter here is actually the perpendicular distance for force T. Okay, so that's why for anti-clockwise moment of T, the anti-clockwise moment is actually the force is T. The perpendicular distance is not 8 meter, it's not 4 meter, it's not 3 meter. It's not 8 meter, it's not 3 meter. It's actually 4 meter. Okay, this 4 meter, where do you find this 4 meter? Is here. Okay, the 4 meter is actually here. Okay, so take note where to get the perpendicular distance and the technique to find perpendicular distance. Okay, so take note of the working. Okay, so once you have it, the anti-clockwise moment with T times 4, clockwise is 1290. Okay, you found 12,900, which you found in the beginning. Do a bit of algebra, you get the answer straight away. Okay, so the technique here that we are looking at is actually finding the correct perpendicular distance. So here, take note. Okay, look, the technique of looking at the perpendicular distance, finding the perpendicular distance is important. Okay, if you need to know more about it, or if you have forgot about it, okay, look at my chapter 5 moments, principle of moments. I have a video on it to show students how to find perpendicular distance. It's just a technique that we have to be familiar with. Okay, explain what happened to the tension if the pile of brick is slowly moved towards P. Yeah. Okay, move towards P. What happened? Okay, so what happened if the brick move towards P? Okay, if the bricks move towards P. Okay, now there are 3 moments that we are looking at. Okay, so there is 3 moments here. We have the anti-clockwise moment. Okay, we have the moment due to the brick. And we have the moment due to the beam. Based on the question, okay, they are balanced at the beginning. Okay, now for the beam here, we are looking at is the moment of the beam, okay, is constant. No matter what happened to the brick, the moment of the beam is constant because it's the same force and the same distance. Okay, it will not change. So what happened is when the brick move nearer to the pivot. Okay, based on the question, it move nearer towards P. Oh, sorry, move towards P. Move towards P. Wrong direction. Sorry. Okay, move towards P. It should be nearer, moving this way. Okay, as I move towards P, certain factors will change. Okay, moment of the brick depends on two things. Moment of the brick depends on the weight of the brick and the perpendicular distance of the brick from the pivot, which is here. Okay, now as the brick move towards P, you will find that the weight actually remains the same. The brick 1,500 remain the same, but as I move towards P, take note, as I move towards P, the perpendicular distance actually increases. Okay, and because my perpendicular distance increases, my moment due to the brick, this number here, will actually be increasing. Can see? So as the brick move towards P, although the brick remains the same size, same weight, all this thing, but the moment due to the brick actually is increasing because the perpendicular distance is increasing. So this number is actually increasing. Okay, so this is constant. So what happened is, as the brick move towards P, and if I have the beam have to be balanced, okay, within the moment has to be the same. Only one thing must happen. You will find that the clockwise moment, because of the brick movement of the brick, the clockwise movement on the right side is actually increasing. So what you need to do is the tension in the rope, okay, which is what we call the anti-clockwise moment, must also be increasing. Okay, I have to increase because I have to balance the clockwise moment. The clockwise moment now is increasing really because the brick is changing position. So the clockwise moment is increasing. So what I need to do is to balance it, my anti-clockwise moment must increase. Okay, and anti-clockwise moment, the rope is fixed, the perpendicular distance is fixed. Okay, so T plus perpendicular distance of T. Okay, so for perpendicular distance T, this is constant. This number is constant. The perpendicular distance is fixed. You can't change the rope. So the only way whereby I can actually increase the perpendicular distance, I can increase the anti-clockwise moment, is to actually increase the tension in the rope. So that's why I have to increase the tension in the rope to balance the cable. Okay, and with that, this is how I deduce what happened to the tension in the cable. Okay, so the whole thing is here. Okay, this is how the reasoning works. Okay, now we look at the keywords. Okay, so in the question, same as the reasoning using the mathematical, okay, using principle of moments, you have to tell the marker that the clockwise moment increases. That's the first keyword that you must write. And you can't say clockwise moment increase straight away. You have to tell the marker what's the reason. Okay, like I mentioned to you, the reason for the clockwise moment to increase is actually the perpendicular distance here. Okay, so in the answer they given, you have to tell me that perpendicular distance of the brick actually increases. And because of that, the clockwise moment increases. And what happened is, you have to tell the marker in the next step is that to increase before you tell me the tension increases, look at the reasoning I phrased a few minutes ago. I have to tell the marker the anti-clockwise moment must increase to balance the beam first. Okay, so that's the train of thought. The process is we look at how the perpendicular distance move. Then after we look at how the clockwise moment changes. Then after we look at how the anti-clockwise moment must change. And because of that, I will be able to deduce the tension in the rope actually increases. Okay, so this is how the train of thought works. Okay, if you look at the answer, okay, not just like the answer just appear from the sky. Okay, the answer that we are looking for is it follows a sequence of reasoning, okay, a sequence of processes. Here, what we are looking at principal moments, clockwise equal to anti-clockwise moment. Okay, but there are processes, the thinking process that's involved. Okay, so look at the train of thought that looking at, and the train of thought will actually tell you how to craft the keywords that is needed in the answer here. Okay, if you're still not sure, okay, you can pause the video and just rewind like to 3 or 4 minutes whereby I look at the reasoning again. After that, watch again. If you have any questions, just drop me an email or drop me a message at the end of the video. Okay, but other than that, okay, this question is a very, very good question. You look at how the students look at the questions, how the students actually analyze the questions and perceive and they use principal moments to solve the question. Okay, question 3. Okay, question 3 is a pressure question. I would say it's quite a straightforward question. Okay, thumbtack, force, it uses the formula force over area, so I will not dwell too much on this question. Question 4, take note, is what I call a heating curve. Okay, heating curve, cooling curve, thermal property. Okay, thermal property, remember the stages of the thermal property, the different stages, different keyword. Okay, thermal property, here we are looking at, very commonly, we always look at two types of energy, the kinetic energy, the internal kinetic energy, and the internal potential energy. And like I mentioned before in the topic thermal property, if I'm not wrong, it's chapter 9 maybe. Okay, there are certain keywords that is tagged to kinetic energy. There are certain keywords that is tagged to potential energy. Okay, so if you have done your revision, you should actually know what are the respective keywords that you should include in the reasoning. You have forgotten, or you have missed them out, okay, look up the playlist, my video on my playlist on thermal properties. Okay, I have actually mentioned in detail the properties for each of the energy that we are looking at, particularly kinetic energy and potential energy. What are the keywords that we need to write at each stages of the property, at the heating cooling curve? Okay, you have to know them. Okay, because at different stages, for example, this is what we call stage 1. Okay, this is what we call the heating phase. Okay, the heating phase, there are certain keywords that you have to mention. For example, at the heating phase, I must mention kinetic energy. What happened to the kinetic energy? What happened to the velocity? What happened to the temperature? At heating phase, same thing. The potential energy actually remain constant. Okay, I must write this in my answer because energy is diverted to kinetic energy. So these are what we mean by keywords you have to write at different stages. Same thing, if I know this is boiling, okay, what we call a stage 4 process. Okay, stage 4 is called boiling. Boiling, same thing. I have talked about kinetic energy, I have talked about potential energy. So there are different keywords to write at different stages. I have actually listed down all the stages, all the keywords for each stages. Okay, so you have to get to know them. Okay, for a question here, this is solid. Okay, so if you look at the phases that we are looking at, okay, solid. Okay, it's always at the beginning is solid. So this will be the heating phase. After that, it will be the melting phase. After that, same thing. After melting, everything become liquid. You will go back to the basic again. I will heat up the thing. So it will be heating phase again. After that, it will be boiling. Okay, the last beyond boiling will be what we call the plasma state. Okay. So at each of the stages, you have to know what happens to the particular particles in terms of kinetic energy, in terms of potential energy, in terms of intermolecular bonds. Okay, so melting point, based on the question, 0 degree, this is the melting. Okay, I would say straightforward. Then what happened to the internal energy? Okay, when the temperature increased from 150 to 170. So look at 150 to 170. Where is 150? Okay, is here. Okay, 150 to 170 is heating phase. Heating phase, we always look at two things. We always look at two energy. We always look at the kinetic energy. Okay, we all look at the potential energy. It's always written in this format. In this particular case, for heating phase, the keywords that we have to write is the kinetic energy. The heating phase always deal with kinetic energy because heating always mention kinetic energy is always faster because at heating phase, these two contribute to what we call the temperature increases. These are the factors that contribute to the temperature increases. So these are what we know. This is what we know by the keywords that you need to write, the respective tagging keywords. And we don't just stop there. Other than we mention the kinetic energy, we also must mention the potential energy. Okay, we have, even though it's constant, you still must mention. Okay, because the conservation of energy, because internal energy consists of two types. two sections. One is internal, one is kinetic energy, one is potential. Okay, so if it's kinetic energy increasing, my potential energy will actually remain constant. Potential energy deal with what? Deal with changes in state. Okay. Then after that, simple PT question. Okay. 15 to 100 minus 15 to 170 kg is 40 kilojoules. 400 kilojoules, not 40. 400 kilojoules, which is 400 with a 30 behind. Assume no heat loss. Okay. What's the power given? Okay. 500 watts. Okay. What does power mention to you? The power formula. Power equal to energy divided by time. AKA energy is power times time. Okay. So if I know that power is 500 watts. Okay. And I know the energy span is going to be 400,000. I will be able to know the time taken. It will be 800 seconds by using the formula. Energy, power is energy divided by time. Okay, I should be able to calculate the answer here. Okay, quite easily done. Okay, now the next question here, we look at the diving question. Now the diver, okay, force produced is 15 Newton. The mass is 70 kg. Oh, it's a straightforward question. Just acceleration produced by 1 kick. The question here is 1 kick. Okay, so take note of it. Okay, so you have the 15 Newton, you have the mass. You plug in the formula, you get the acceleration, 0.214 meter per second squared. Okay, now the refracting index. Okay, remember the formula. Refracting index. Okay, there are two formulas to calculate. One is the angles, in terms of the angles, the trigonometry, angle in the less dense medium divided by angle in the dense medium. The other formula for refracting index is actually the speed in vacuum divided by the speed in the medium that you are of concern. So these two formula is needed. If you look at refracting index, you must know this formula because there's no way we can reproduce or derive this formula, okay, at your level. Okay, so if you know the formula, okay, see the symbol for vacuum is actually C. This is the symbol we commonly is V. So if you know the formula, you actually know the answer straight away. Just substitute the formula, substitute the equations, you get answer straight away. Okay, speed of air is 3 times 10 to the power 8 meter per second. Water is 2.3 times 10 to the power 8. So you substitute inside, you get the answer straight away, 1.3. Okay. Speed of light. How speed of light bend? Okay, drawing of light ray. Okay, drawing of the light ray, complete the light ray. Same thing, air. Most students will know this is less dense. Water will be the dense medium. Now, here the question here mentioned is the flat and the diver. So you must make sure the light must go to the diver. Okay, so you can choose any part of the flat, basically. Okay, so the moment the ray hits the surface of the water, there is a normal here. So what we are looking at is that the ray that you draw must bend in the right motion, in the right direction. Okay, remember, dense to less dense, dense to less dense. Okay, the ray must bend towards normal. Okay, so it must bend towards normal. Okay, which is what the picture here mentioned. Okay, this ray bends towards the normal, and also it must enter the eye of the diver. Okay, then after that you get a 1 mark straight away. Okay, it's a simple 2 mark question or 2 mark question. Now, same thing, how we explain the path of the ray. Now, path of the ray is, we always mention the keywords when we talk about bending of light. You always deal with two things. You have to tell the students, you have to tell the marker what medium the light is coming from. Okay, then after that you have to tell where the light ray bend, and after that, okay, you have to tell them the reason. Okay, it's because of the speed change. Okay, what change you have to mention? If I bend towards the normal, okay, it means that the speed of the light actually slow down. Okay, so if you look at the keywords to explain ray bending, okay, it's always the same 3 things that we always mention. Okay, we always tell the marker. Okay, the first thing that you must always tell the marker is how the medium changes. Sometimes medium change is given in the question. Okay, for example, air to water or this thing, but I will say it's safer to mention that actually to tell the marker, say you know that the water is a denser medium. Okay, then after that you have to tell the marker how the light ray bend towards and what's the cause of it because of the speed of the light ray. Okay, so this is like what I mentioned here, speed slow down, bend towards normal. Okay, if you want to play safe, okay, other than mentioning the water here, you can finish off with water, which is the denser medium. Okay, just to let the marker know that you know it is actually traveling from less dense to dense medium. Okay, so I will actually include this phrase at the back of the question here. So these are the three things that I will tell the marker every time I try to explain how the bending of light occur at different medium. Okay, first thing I look at is the direction of the traveler, less dense to dense. I will tell the marker how the light ray bend, and after that I'll tell the marker what causes the bend, the speed, the change in the speed of the light itself. Okay, these are the three keywords that I always mention. Okay. Okay, now we look at question 6. Okay, question 6, one of the things that you have to be careful in the question is that there's a mention of the word constant speed. Okay, the moment you see constant speed, there are some inferred meaning behind it. Example, you will know that the acceleration is actually 0 meter per second square. And when I know the acceleration is 0 meter per second square, I will also know that the net force applied on the object will also be 0. These are what we mean by common clues in the question. Okay, or sometimes that I also can infer that maybe the question is trying to tell me maybe there's no change in kinetic energy. Okay, so these are what does the word constant speed mean? Okay, the meaning behind the sentence there. Okay, so what happened is state the magnitude of the weight of the anchor. Okay, and explain how I derive. Okay, the weight of the anchor. Okay, the weight of the anchor, because I know the resultant speed is 0, so definitely, okay, because the resultant speed is 0, I will definitely know that the force applied and the weight will be the same number. Okay, so which means because the resultant speed is 0, so the force applied must balance with the weight. Okay, so the force applied, okay, and the weight, the resultant force of these two will give you 0. So which means I will know that the weight will actually be the same value as the applied force, which is 300 Newton. So that's why I know the answer here will be weight will be 300 Newton straight away, 2 marks. Okay, and why do I know that? Like I mentioned to you, because I know A constant speed means A equal 0 meter per second square. I know the net force is 0, and from there I will know that these two number is the same. So like I mentioned before, this is the keywords that you must mention. Okay, so do I want to mention the weight and the applied force is the same? Yes, I may want to apply. So I may want to write. So maybe here, before I write 300 Newton, then maybe I can just say the force applied is same as the weight. Okay, so then after that, I'll tell the marker the weight is actually 300 Newton. Okay, remember to write the value. Okay, so even though I say same, but it doesn't mean I never say the value, I will not be answering the question because the question says state the magnitude. So I must write down the number. Okay, work done. Okay, force applied and the distance traveled. Force is 300 meter, distance is 8 meter. So you get the answer straight away. Nothing difficult about it. Now the question says the motor is 12 volts, current is 10 amp. Oh, there's a 8 meter. Okay, it's 25 seconds. So the energy converted. So the energy transferred to the motor to raise the anchor. Okay, what's the energy I need to raise the anchor based on the motor? Remember here we are talking about the motor. The motor need 12 volts, current is 10 amp, and distance. The time is 25 seconds. So the formula that we look at is power is energy divided by time, and after that energy is power times time. But I don't stop here because I don't have power yet. So what I do is I break down power. Power formula for power is current times voltage. Okay, which is IVT, which is how I derive at this formula here. Okay, so after that, I substitute the current, I substitute the potential difference, time 25 seconds, I will get 3,000 joules. So this is the energy input. This is the energy input by the motor. What does it do? It used to do work, okay, to leave the anchor. So this is actually what we call the energy output. Okay, so after that, there's definitely a loss, okay, and the loss of it will be the difference between them. I will get a loss of 600 joules. So it could be energy due to the current to overcome the current, or it could be energy loss due to the motor itself, the internal parts. Okay, sound wave. Okay, here we look at is earthquake. Okay, and here we look at if there are two sensors. Now, here what happened is observe that the particle move in the same direction as the earthquake. Okay, remember definition of sound wave. Okay, there are two types of sound, longitudinal and transverse. Okay, but based on the questions, moving in the same direction as the vibrations and the motion as the vibration move in the same direction as the wave motion, you only mean one thing. It only means that this wave is actually a longitudinal wave. Okay, aka it could be a sound wave, a shock wave, we call it. Okay, then after that, sensor A, which is here. Okay, it's nearer to the earthquake zone. It takes 3 minutes and 48 seconds. Remember SI unit. Okay, then after that, sensor B, it takes 4 minutes and 17 seconds. Okay, and the distance between A and B is 200 meter. 200 meter. Okay, so this is 200 meter. Sorry, wrong number. 200 meter. Okay, so calculate the speed of the wave. Okay, it's quite easy. Not 200 meters, sorry. 200 kilometers, sorry. Okay, so take note of the SI unit. And for sound wave, remember when you look at sound wave, one of the common formula that we use if you like to use speed equal distance by time, because sound is a constant number. Speed of sound is constant. Okay, so you know the speed is, you know the distance is 200 kilometer. Okay, then after that, you know that the time taken is here, seconds. Okay, the time taken is second. Substitute the number in, you get the number. And the marker is being kind to you. He would just want the number to be kilometer per second. So you don't even need to change the unit for distance. Okay. Wave motion. Okay. Wave motion, take note. Okay. Wave motion, here we are looking at two particular things. Okay. We are looking at the amplitude, the middle, the equilibrium to the peak, the equilibrium to the peak. Amplitude here refer to where? The loudness. What am I writing? Amplitude here refer to the loudness. Okay, the higher is the amplitude, the louder is the sound. The second thing, when you look at curve, sound wave, okay, we want to look at actually is the period. Okay, the period of the curve here, the period of the wave itself. Okay. Why? Because the period control your pitch. Okay, sometimes we don't look at it as period. Sometimes we look at it in terms of frequency. Okay, but frequency and pitch, they have period and frequency, they have the inverse relationship. For example, most of us will say that the higher the frequency, the higher is the pitch. Okay, or sometimes we just reverse it. We just say the lower the period is, the higher is the frequency. So it depends on how you want to look at it. But one thing for sure is that the frequency and the period actually determine the pitch. Okay, so based on this, you will know that based on the question here, we are saying that the two graphs, okay, in terms of magnitude, they are the same. In terms of magnitude, they are the same. 2 square. So they are actually the same loudness. Okay, so difference between them is actually the period. Okay, sensor A has a louder, has a bigger period. Okay, has a bigger period. Sensor B has a lower period. Or sometimes we say that sensor B has a bigger frequency. Okay, so if you look at period of B, period of A, they are bigger than each other. What does this mean? It also means that the frequency of A is actually smaller than frequency of B. Okay, and because frequency and pitch, they are related. Okay, so whoever has the higher pitch or whoever has the higher frequency will have the higher pitch. Okay, this is how I infer the answer. Okay, let's look at how I look at it. Sorry. Look at how I infer the answer from the graph itself. Look at what the questions need you to find and what does the particular topic need you to understand. Okay, in this case, we look at it in terms of amplitude, we look at it in terms of pitches. Okay, the frequency. Okay, we look at frequency, we look at pitch, we look at amplitude, we look at loudness. EM spectrum, nothing much. Okay, I will skip this question because it's quite a straightforward question. Okay, so remember for EM spectrum, one thing that you have to remember is please know the arrangement of the spectrum. Please know the type of waves and their users. Okay. Isolated charges. Okay, electric field. Okay, electric field pattern of two charges. These are plus and minus. Please look at the pattern in your textbook. Okay, know the pattern. Okay, draws symmetrical field lines, all these things. Okay, so these are the common things that you take note when you draw field lines. Okay, please know the correct direction. Field line is always drawn from, the arrow is always pointing from the positive charge to the negative charge. Okay, field lines. The field lines, okay, the closer it is, the stronger is the field line. Now, question 10. Question 10 is a density question. Now, based on information, you are given the mass of the empty tank. Then after that, you are given the volume of the oil and the density of the oil. Okay, so take note of this. The moment you talk about volume and density, you'll know that the formula density is actually mass divided by volume, or mass per unit volume. So if I give you the volume, I give you the density of the oil, actually I'm indirectly giving you the mass of the oil is given already. It's just that you may want to do a bit of working here. So the mass of oil is given. Okay, state one differences. Part 8, state one differences between mass and weight. Oh, it's a fairly straightforward question. Okay, it's easier. It's one of the, I think most of the textbook and notes. Okay, we teachers actually give you a table, just know them lah. Calculate the weight of the tank when it's full. So it includes oil and tank. So same thing, like I mentioned to you, you actually know the mass of the oil already. Okay, so that's why with these two nut value, you know the mass of the oil, and after that, you know the mass of the tanker, which is 3000. Add them together, you will have the total mass of the tank. Then after that, same thing, weight is mg. Okay, so you must multiply by g. So that's where the tank come in. Okay, so yeah, it's quite straightforward here. Section B, okay, choosing a section B, choose two questions. Okay, on the day of the exam, okay, choose two questions. Okay, just take note, okay, choose two questions. So don't start straight away at question 11. Okay, at question 11, 12, and 13, please read through the question, choose the correct two questions. The question that allow you to secure the most mark, that is the question that you want to choose. Okay, don't just choose question 11 because it's the first question or because I like kinematics. Okay, look at the questions that you are looking at. Okay, read through all the questions first before you choose the correct two questions. Okay, choose two questions. You have to choose. Don't expect the marker to choose the question for you. Okay, so read carefully. Now, question 11. Okay, I jump on the plane, parachute jump on the plane at A, which is here. Okay, then after that, he activates parachute at C. This is where I open up the parachute and he lands on the ground at D. Okay, nice landing. Okay. Now, he activates parachute at C and he lands on the ground. Okay, initial acceleration. Now, I jump off. This statement here tell me a few things. The moment I'm jumping off the plane, I'm experiencing what we know as free fall. Free fall, common characteristics, the acceleration is actually the gravitational field strength, which is the acceleration due to free fall, which is 10 meters per second squared. which is why I get this number straight away. Calculate the height above the ground where the parachute opened his at sea and before he reached. Okay, so I want the height, which aka I want the distance. First, check. Okay, I have what graph am I looking at? Speed time graph. Speed time graph, same thing. If I have a speed time graph, two things that I'm concerned with for me is I want to know the gradient, because the gradient will tell me the acceleration of the object. Second thing I want to know is the area under the graph for speed time graph. Why? Because this area will give me the distance traveled by the object. So from C to D, okay, effectively is from here all the way here. So this area here, I want to know this area. Okay, so this area, why do I want to know this area? Because this area will allow me to calculate the distance traveled that I want. Okay, so this area is the one I'm concerned, which will allow me to find the distance which I can travel. We had traveled between C to D. So that's why I look for the area for the shape here, which is a triangle, which is half base times height. You look at the number, look at the graph, you get the number straight away. Okay, so this is how I get the formula half base times height. This is where the half come in, because the area I know is a triangle. Given the mass is M, okay, everything is M. Right now, expression of total energy at C. Now, total energy at C, I'm at the highest point here. I have a point, not highest. I'm at a point on the air. There's above ground above me, and I am traveling at a certain speed. So at C, there's definitely kinetic energy, and there is definitely potential energy. Okay, so that's why I will be able to calculate the kinetic energy and the potential energy, and I will calculate the total energy. Okay, now same thing, MGH. I know this is 48. Where do I get the MGH? 48 is from here. Okay, the beginning. Okay, so the mass expression is 480. How do I know the speed? Where do I know the speed? 12 meters per second square. How do I know the speed? Look at the graph. The graph is here. Okay, this is the 12 meter based on the question. Okay, a lot of students who do this question, you can't, a lot keep saying that you can't find the speed. You actually have the speed. It's actually at, the question say at point C, you have the speed which is 12 meters per second. So take the value from the graph and you substitute into the equation, and you get the two number. Okay, 480 plus 72, it will be 552 M. In terms of M, okay, calculate the speed of the question just before he hits the ground. Okay, just before he hit the ground, remember, between there's no energy loss, so between all the energy at C must be converted to all the energy at D. Energy at C is actually kinetic energy plus the potential energy at C. Okay, it's all converted to kinetic energy at D. Okay, so the kinetic energy, total energy at C and potential energy at C, where do you find it? It's actually here. Okay, so you actually have this formula, 552 equal to half mv squared. You do a simplification, you get the answer 333.2 meters per second. Okay, quite easily done, I would say. Okay, just remember, see the graphs. In this question here, part C and part B actually require you to read from the graph, infer the value from the graph. Okay, state the principle of conservation of energy. I will not dwell too much. Okay, this is a very standard definition. Now, explain why the sum of kinetic energy at C is only 80% of it at A. Okay, what happened? Okay, where you find that the total energy at C, the total energy at A. Okay, why? They are not the same. How are they not the same? The total energy at A is actually higher than C. Okay, because there's a 20% loss. As a result, the energy is only 80% only at C. Why? Okay, same thing. When you drop through the sky, there will be losses. Okay, because there will be air resistance, you rub against the air, all these things. So all the energy, some of the energy will be actually converted to heat energy as you fall through to reach C. Okay, so in real life, it doesn't mean, in theory, it's ideal. Yes, we always say energy is always conserved, but in real life, it's also conserved. Okay, but just that it's not 100% given to a particular stage. Okay, some energy actually split to other stages like what? Heat loss. Okay, so there will be the heat loss at the in the process. So when you look at the energy, okay, the energy at sea in real life, okay, is not just kinetic energy at sea, it's not just potential energy at sea. In real life, you actually have what we call your losses. Conservation of energy is still conserved, but just that it may not be so straightforward as in just given to EK and EP. Okay, so there will be one more thing that's appearing, will be your losses. Could be the air resistance, it could be sound, it could be other things that are contributing to your losses. Okay, so that's why the energy actually is lower. Okay, parachute in terms of forces, okay, motion of B to C. Okay, now let's go where's B to C. Okay, B to C. Okay, now B to C is these particular stages here. B to C, yeah. One thing for sure, you look at the question here, the B to C, the gradient is actually getting gentler and gentler. The gradient is actually getting gentler and gentler. So between from B to C, if you look at it in terms of speed time graph, you'll find that the gradient is getting gentler and gentler, aka the acceleration experience is actually decreasing. That's what the graph is trying to tell you. The gradient, okay, it has to everything to do with acceleration. So the gradient getting gentler and gentler, or what we call the gradient is getting smaller and smaller. Okay, it's because why? And what does this mean? It means the acceleration is getting smaller and smaller. And when accelerations get smaller and smaller, what does this mean? You actually infer that F net equal ma, Newton's law. When the acceleration gets smaller and smaller, it will mean that the net force experienced by the object will also be getting smaller and smaller and smaller. Okay, so what does this mean? Okay, now this is what we mean. Okay, which means the acceleration is, this is what I mean by the acceleration is getting smaller and smaller. Okay, so when you talk about F nets and that particular junction, okay, your acceleration is getting smaller because, and what does it mean? It means the resultant force is getting smaller and smaller. But how does net force get smaller and smaller? The parachute is having the same mass. Okay, the parachute is here. Okay, the mass is always constant. The weight is always constant. But what happened is that the air resistance is not constant. As I go down, as I drop faster and faster, my speed increases. My air resistance will actually be increasing. Okay, and net force is contributing by where? Net force contribute F weights minus air resistance equal to ma. Okay, so what happens as I fall from B to C? As I fall from B to C, my weight is constant, but my air resistance actually is increasing. It's getting bigger and bigger. So the difference between them is actually getting smaller and smaller and smaller. And as a result, okay, the difference getting smaller is aka what we call, what they do? Okay, the net force is getting decreasing. It's getting smaller and smaller because my air resistance is getting bigger and bigger. Okay, because as I go for faster and faster, remember air resistance is proportion to speed. Speed increase, my air resistance will get bigger and bigger. So as I keep falling down, as my speed keep increasing, my air resistance actually get bigger and bigger. And when air resistance get bigger and bigger, the difference between the two of them will actually be smaller. And because of that, my acceleration will actually be smaller and smaller, okay, due to the air resistance changes. Okay, and this is what we mean by the changes in the forces. So sorry. Now, question 12. Okay, question 12 is a heating question. Okay, take note of the of the labeling. Okay, milk bottle, shiny casing. Okay, foam. Okay, heating element. That's where the heating element is at the bottom. They may be telling you something about convection current. Foam usually tell us the material. Maybe it tell us about conduction. The material will deal with conduction. Maybe the heating element, the location. Maybe it tells us something about the convection current. Shiny outer layer. Shiny outer layer is definitely is about texture, surface, the texture. Shiny texture is definitely about radiation. So this is what the question is trying to tell you. Okay, how heat is being transferred. And maybe there's a cap here. Okay, maybe talking about convection also. Okay, so this is how I deduce what type of motions, what type of heat loss the question is trying to hint to you. Okay, the labeling actually tells us what type of heat loss is experienced by the object here. Okay, for example, foam field. Foam is conduction because foam actually means air. There's presence of air, and you have to tell the marker air is poor conductor and conduct heat away, okay, at a slower rate. Look, remember the tagging keyword lah. If I use conductor, I must use the word conducted away. Okay, conducted. Okay, conductor, conduct. So try not to use the word transfer or lose. Okay, this is what I mean by tagging keyword. If I use shiny, it has to be radiation. It is emitted, the heat must be emitted. Okay, if it's an absorber, it must be absorbed. Okay, so these are what I mean by the tagging keywords. Okay, that it happens in the mode of transfer. How energy is transferred from the heater to throughout the water, not the milk bottle, everything is throughout the water. Throughout the water, it has to do with the heating element, the location. Okay, and location it deal with convection. Convection only deal with two things. Okay, hot versus cold. Okay, hot, when you talk about hot, you definitely have to mention a few keywords. When you talk about hot, okay, you talk about hot, you have definitely talk about less dense and rise. Okay, the density, you have to mention the density. And same thing, you talk about cold, you talk about the cold, you must talk about the density, and you talk about sink. Okay, so here we don't just use the word hot rise and cold sink. You tell me hot rise, why? Because of density, less dense. You talk about cold sink, why? Because it's being denser. So you have to mention about the density. Because convection current occurs because of differences in density. So the density mentioned, the density is actually one of the most important factor. Okay, then after that you talk about convection current occur. Okay, allowing heat to be transferred. Okay, so these are what we mean by the three keywords that we look at: hot, density, less dense; cold, denser; sink. Then after that, you mention about convection current occur. So these are the three keywords that we always mention. Remember, keywords. One keyword doesn't mean one word. It could be a phrase. Okay, so power is 230. Power is 200 watts. Potential difference is 230. Okay, current flowing through the heating element. Straightforward formula, P equal IV. Now, why is it not safe to use when the fuse fitted to the neutral cable, live cable? Remember what are the keywords when we talk about electrical precautions? Fuse. Okay, fuse has always has to be connected to the live cable. Okay, why? Because why is it connected to a live cable? Because if it's live cable, when it melt, it can disconnect the appliances from high voltage. So what happens is when it's connected to the neutral cable, it will mean that when the fuse breaks, okay, when it melts and breaks, this one the keyword, the appliance is still at high voltage. It's not disconnected one. Okay, so when a person touch, you will still be electrical shock. Okay, so same thing as I given to you when you explain fuse, the proper fuse in the live cable, you always have to tell the marker that why fuse is useful, because it melt and break, and after that you can disconnect from high voltage. So these are the keywords that we always write. Particular section here, right? We look at the costing. Okay, so whenever we look at cost of electricity, we always work from the angle of energy first. So energy is power times time. Okay, so when we look at cost, we need the energy use. Whenever we look at the energy use, okay, we always like to keep the unit for power to be kilowatt. The time used to be in hour. Because when we look at costing, right, we always look at energy use in terms of kilowatt hour. Okay, so that's why when we look at energy, you'll find that we actually purposely change the power, let's say from watts to kilowatts, from seconds, we actually change it to hour. Okay, because of the unit that require for costing is actually kilowatt hour. So now based on the question, right, we have 30 days, and the total amount of energy, total amount of cost we need is 0.96 cents. So we know that the each kilowatt is 32 cents. So from these two number, right, you will be able to derive that the total energy used for that day, for that 30 days is actually 3 kilowatt hour. Okay, 3 kilowatt hour. So now if you look at, if I use 3 kilowatt hour, from here I will be able to derive how much time I use, because based on the question at the beginning, the question got mentioned already, the energy use, the power of the heater here is actually 200 watts, which is 0.2 kilowatts. So if I have the total energy use, which is 3 kilowatt hour, if I know the power use is 0.2 kilowatt, I will be able to locate the time spent or the time used in the days, in these 30 days. Okay, so this is how I derive this formula here. Okay, so just take note, when we look at costing, right, if you look at the cost of energy, cost of using energy, of electrical energy, when we talk about costing, is always started from kilowatt hour. Okay, kilowatt hour energy is calculated in terms of kilowatt hour, and when I need kilowatt hour, one of the common things that we have to be careful is that we don't use the SI unit watts. We purposely convert power to kilowatt, and we purposely convert time, okay, to hour, okay, for the ease of calculation. So take note of the formula here. Only this formula is slightly different, okay. Most of the formula that we use in physics are actually in SI unit. Only like this particular formula is not in SI unit. So take note of it. The last segment here for this question here, D, is they will explain why the increase is actually much faster. Why does it take more time for the milk to increase, from 30 to 40 degree as compared to 10 degree to 20 degrees Celsius? Okay, here to take note, right? When we talk about temperature change, okay, temperature change, one of the important things that we need to take note is the direction of change. Temperature always change from where? From hot to cold. Okay, hot to cold region. Okay, that's how the temperature will transfer. Okay, it's always go from hot area to cold. It's always losing energy from hot to cold. Okay, so and the other one that we take a look is at how fast it travel, how fast the heat actually transfer. Actually depends on the difference in temperature. Okay, for example, right, the ambient temperature, the environment temperature, let's say it's room temperature is 34 degrees Celsius. Okay, so the bigger the difference between you, me, and the environments, the faster it will be the rate of transfer. So for example, if the temperature is 10 degrees Celsius, okay, so the difference between the object and the ambient temperature, 34 degrees Celsius, is actually 24 degrees Celsius. Okay, versus let's say based on the question is 30 degrees Celsius. Okay, so if I'm already at temperature of 30 degrees Celsius, okay, the difference between me, the object, and the environment temperature is here now is 4 degrees Celsius. Okay, so you find that even though, right, we start from 10 degrees Celsius, I start from 30 degrees Celsius, I want to increase by 10 degree, or I want to increase by 4 degree. You'll find that for the same temperature change, if I want to increase by 4 degree, to increase, let's say, not say 4 degree, 2 degrees Celsius, okay, to increase 2 degrees Celsius. Let's say for both cases, I want to increase by 2 degrees Celsius. I want to increase by 2 degrees Celsius. Okay, you'll find that for the first case, if I'm at 10 degrees Celsius, you find that it's easier for me to increase by 2 degrees Celsius because the temperature difference between the object and the environment is actually much, much bigger. So there's actually more room for changes, more room for increment. So as a result, because of this bigger room in increment, the time taken to increase is actually shorter. It actually allows a faster change in temperature. So you find that if I'm actually 30 degrees Celsius already, if I want to increase by 2 degrees Celsius, Okay, if I want to increase by 2 degrees Celsius, you'll find that because the temperature between me and the object is actually not, and the me and the environment, the object and the environment is not a lot. Okay, and if I want to increase by 2 degrees Celsius, and because the difference between me and the environment, the object and the environment is actually quite small, to increase that 2 degrees Celsius is actually very, very difficult. Okay, and because of that, it actually take a longer time for me to increase the same 2 degrees Celsius, because the difference between the object and the environment temperature, the change in the difference in temperature is actually smaller. The smaller the temperature differences, okay, the harder it is for me to increase the temperature. Okay, so let's say if my temperature is, let's say, 20 degree, it's 40 degree apart. Let's say it's 40 degree apart. Okay, so I'm a very low temperature. I have a bigger change in temperature versus the another object who has a smaller temperature differences. The one with the bigger temperature differences will increase temperature at a faster rate. Okay, so when we talk about heat transfer, we have to remember one thing that we always need to take note is the direction of travel is always from hot to cold. The other thing that we need to take note is actually how fast the direction travel. The faster the direction travel, it depends on a few factors. It depends on the medium. It depends on the mode of transfer and color of the object itself, and also it actually depends on the difference in temperature between you, the object, versus the environment temperature. How far are you away from the room temperature? The bigger the differences, the faster you will be able to change. That's why we look at the temperature changes. The loss or the change in temperature is always greater, okay, for object with a lower temperature. Okay, so that's why we have to always remember these two. Okay, so the bigger the temperature differences, the bigger is the rate of change of temperature. Now, question 13, I would say, is an interesting question that we don't usually see in electrostatics. Okay, it's a gold leaf electroscope. Okay, what happened here is that in the Perspex rod that is given, okay, the Perspex rod is positive charge. Okay, it's a positive charge. So it is being brought near to the brass cap. Okay, so this is a Perspex rod, which is positive charge. It's brought near to the brass cap. Okay, what actually happened now is this. Okay, so the question breaks down into two parts. First, part A, he talked about the Perspex rod first. Okay, when how is it being positive charged after rubbing a rod? After rubbing with a cloth, I would say it's a standard answer for charging by friction. Okay, based on the question, if I'm positive charge, I must lose electrons, okay, to the cloth. Okay, and as a result, because if I lose electrons, I will become more positively charged. Remember, the keyword here is the electrons. You must lose electrons because electron is lighter, it's easier to actually dislodge from my atomic structure. Now, the other second segment that we look at is after the Perspex rod is brought to near to the brass cap, what actually happens? Okay, you'll find that actually when the Perspex rod move nearer to the rod, to the brass cap, the gold leaf actually swing. He actually opens up. The gold leaf actually opens up. Okay, what actually happened was this: when the Perspex rod is brought near to the cap, okay, originally the gold leaf is actually here. Okay, he has not swing in it. It's just lying straight down. Okay, he has not swing, it's uncharged. What happened when the Perspex rod move nearer to the brass cap now? Okay, what happened is this: the free electrons in the gold leaf in the brass plate here, the free electrons, the negative charges, will actually be attracted towards the Perspex rods. Why? Because opposite charge attract. Okay, so what happens is when opposites attract, these electrons will actually move up to the surface here. Okay, so what happens is when I move up, after I move up, okay, after the electrons move up, what is left behind at the gold leaf here is actually all the positive charges. Okay, remember it started out with uncharged. The gold leaf electroscope at the beginning, the gold leaf, the brass plate, everything is uncharged one. What happened now is because the Perspex rod is brought near, and the electrons from the gold leaf actually move up. Okay, the electrons move up. And because the electron now has actually moved up to the surface because opposite charge attracts, what is left behind is actually all the positive charges. Okay, so actually left behind what is the positive charges. And because there's all the positive charges are at the bottom now, you'll find that this is what we call light charge. Okay, and because the light charge, they will repel each other. And as a result, okay, you'll find that the rods will actually, the leaf will actually swing away because all these are light charges. Okay, so it will repel up. Okay, then after that, the gold leaf will open up. Okay, and this is what we mean by deflection. The gold leaf will be deflected from the brass plate. Okay, this is what happened to the whole process. It's a process of 1, 2, and 3. Okay, so when you write your answer, you have to write these 3 steps. Okay, where I talk about the gold leaf, the electrons move up. Okay, because unlike charger attracts. And after that, you have to find that the brass plate will be the brass plate and the gold leaf at the bottom. This refer to the bottom, will be positive charge and it will deflect. So these are the 3 keywords, that 3 sentences or 3 keywords that we look at when we look at electroscope, the gold leaf electroscope. Which is a quite interesting experiment. Okay. The rest here will be I would say the standard formula whereby you look at your charges, current equal to Q over T. Okay, the charges flow is 0.025 coulombs. Okay, after that, you'll find that the time taken here is 0.01 milliseconds. I remember milli is 0.01 times 10 to the power minus 3 second SI unit. Okay, so 0.025 divided by the time taken, you have the current flowing through the brass plate. Okay, so this is what actually happened. Okay, so what happened is, like I mentioned in part B, okay, it's extension of part A. After the plate is actually moved up to the surface, if I'm going to put a cable at brass cap here, I will be able to direct all the electrons out from the surfaces. And when the electron flow down from the brass cap, it will be in terms of current. Okay, and same thing, the voltages of the brass cap. Okay, same thing, what's the formula? Potential difference, other than V equal IR, there's another formula called energy divided by charges. Okay. Energy divided by charge. Oops, no ink. Give me a minute. Okay, the other formula that we look at is energy divided by charges. Okay, not just V equal IR, and a potential difference, there's another formula is energy divided by charges. Amount of energy, the question has given. Okay, 10 joules of energy is being released in the process. Number of charges given is 0.25. Okay, so you plug in the formula, you get the potential difference is 400 volts. Okay, now the brass cap is earth using wire B. Okay. Okay, now it's same material, but it's twice the length. Cross-sectional area is half of it. So here we look at another formula, which is the resistance. Resistance is rho L over A. Rho here refer to the resistivity. It refer to the resistivity. Same material. So let's take a look. How do we take this? So if it's same material, it refer to the resistivity. Then after that, we look at the length, refer to here, this factor. And we look at the area, cross-sectional area here. Okay, so these are the 3 factors that we deal with. So you mentioned that B is same material, so this number is the same. So A and B will be the same. Length B is, wire B is twice, okay, and its cross-sectional area is half of that. Okay, so this is twice the length of A, and the area is actually half the area of A. Okay, so you find that if you look at the factor here, because of the half here, you'll find that, okay, 2 divided by half, it will give you a 4. Okay. So you'll find that the resistance of B is actually 4 times the resistance of A. So that's how I'm able to deduce that it is actually 4 times of A by using the formula that's resistance is rho L over A. Okay, so you have to remember what is the general formula for electricity, V equal IR. But other than that, you also must remember the individual formula, okay, for voltage, current, and resistance. Okay, if not, you will not be able to solve this question one. Okay, and after that, same thing, calculate the current flowing through using Ohm's law. Okay, so if the voltage remain the same, my resistance is 4 times, my current will be a quarter time current flowing through. Okay, because why? The higher the resistance, the lower the current. Okay, so with this will be the last question that we deal with for this particular topic here, this particular paper here. Okay, if you need any other questions or if I have explained anything wrongly or any feedback, okay, feel free to leave your comment below. I also like to know about it. Okay, if not, you can drop me an email. Okay, so in the next few days to come, I will be uploading some papers for other revision paper that I given to my students. Okay, then after that, I'll upload it to the YouTube channel. So if you like to receive notifications about this paper when I upload, remember to subscribe to the channel and also to press the bell button so that you get any notification from me, okay, whenever I upload the paper. Okay, if not, it being a long video. Okay, so enjoy.